In this video, we are discussing the intuition behind the Principal Component Analysis technique. Principal Component Analysis, or PCA, is a feature extraction dimensionality reduction technique. It extracts features that are a linear combination of the original set of features. These linear combinations are the new features that better explain the data in a more compact form. PCA is an unsupervised learning technique. Therefore, PCA does not consider the labels of our data points. PCA only considers the features that represent each data point in space. In the example of apples and oranges, PCA will only look at the features, weight and greenness, without taking into consideration if it's actually labeled as an apple or an orange. The main idea behind PCA comes from its name. Principal Component Analysis breaks down a given dataset into its principal components, or main building components. These principal components are then used to describe the data and reduce its dimensions, keeping only the building blocks or principal components that contains most of the information about the data. These building blocks or principal components are the directions in the data that contains the maximum variances along them. In the apples and oranges example, PCA will choose the first principal component of the data as the direction along this orange ellipse. This is the direction with the maximum spread of data, which is the direction of the maximum variance. We can break the PCA technique into two main steps: understanding and description step and dimensionality reduction step. You can think of it as summarizing a book. First, you need to go through the whole book to identify the important chapters and sections. That would correspond to the PCA understanding and description step. Then, you can summarize the book into only the important parts. That would correspond to the dimensionality reduction step. The criteria used to define the importance, again, is the amount of spread or variance along a direction in the feature space. Let's take this example. We are researchers in an R&D department of a coffee company. We want to know what is the best recipe for a cup of coffee. Our dataset is only measuring two features for each cup of coffee studied. On the x-axis, we have the number of coffee spoon per cup. On the y-axis, we have the number of milk capsules used. One pre-processing step is done on the data points, which is centering the data around the origin. In other words, making the data zero mean. This makes our calculation easier to perform. We want to describe this dataset using the variances along the given features. From the plot, we can notice three things. First thing, the data is spread over the x-axis more than it's spread along the y-axis. Secondly, the maximum spread is along the diagonal direction. The third observation is there seems to be a relation between x and y. It seems like an inversely proportional relation. When x increases, y seems to decrease. In more technical terms, variance along the x-axis is large, variance along the y-axis is smaller, variance along the diagonal direction is the largest. There is a negative covariance between features x and y. If we use PCA to do the description step for us, it will return almost the same information that we noticed, which is the direction of the maximum variance is along the red diagonal line. PCA will label this direction as PC1, or the first principal component. PCA will also return the perpendicular direction, which contains PC2, the second principal component. That is the second orthogonal direction to PC1, or perpendicular direction to PC1, that contains the second largest variance in the data. Since the data is originally in 2D, we do not have any more orthogonal or perpendicular directions that might contain variances of the data. The idea of PCA is to represent the same information in the data in a more optimal way. One way of seeing PCA description step is that PCA finds a rotated version of the original axis. Those rotated versions of the axes align better to the data variance, so that the rotated x-axis is along the direction of the maximum variance. Then instead of having features x and y to describe the data, we are now using PC1 and PC2 to describe the data. PC1 and PC2 are just the rotated version of the original axis. This is the intuition behind the data description step of the PCA dimensionality reduction technique.